Howdy, my name is Jian Tong. I'm an assistant professor from the School of Performance, Visualization, and Fine Arts. And I'm also assistant director for project development at Texas A&M Institute of Data Science. So in this module, I'm going to talk about the frameworks for deep learning. And we'll start by a brief introduction to deep learning. And then we'll go into some details about some applications and also the framework used to deploy and develop and deploy applications in deep learning. So before we get into the materials, I want to recommend two very good references. One of them is a book written by Ian Goodfellow, Yoshua Bengio, and Aaron Collier. So they are leading experts in deep learning, and this book actually is one of the best references you can find about deep learning related materials. And you can download the book for free, or you can buy a hard copy from some vendors. Another reference I'd like to recommend to everyone is the animation of neural networks. Those animations were done by Grant Sanderson, and you probably have already watched his videos at 3 Blue 1 Brown YouTube channel. There are many other related animations for linear algebra and other concepts. Those are very good for getting started with neural networks and some other basic mathematical concepts related with neural networks. So deep learning is part of the machine learning methods. You can consider it's a subset of the machine learning methods. And the machine learning methods are considered as an approach to achieve AI. And artificial intelligence is a big umbrella under which you have robotics, machine learning, data mining, and all the other related research. But as far as deep learning is concerned, it's one of the techniques to implement machine learning. And we'll learn a bit more about that today. And actually, there will be another module about traditional machine learning methods, which will cover some basics of regression models and clustering methods and supervised learning methods. So deep learning is one relatively new but very powerful method, and we'll learn more about it today. So for machine learning methods, you can consider it's kind of different from the traditional modeling modeling methodologies for scientists and researchers to study the natural phenomena or anything that could be built up as a mathematical model. So the basic idea is that you start with a limited amount of data, and then you pose some hypothesis, and then you derive your mathematical equation based on the data you're collecting, and you can verify and validate your mathematical model and continue improving it until the model is good enough to make good predictions. And with the help of a computer, you can plug in your data and implement your scientific model into software, and then you can use a computer to make predictions. So that's a traditional way of doing modeling. Tradition in the sense that it's the way how all the science and engineering applications have been carried out with the help of computers. Now, there's another paradigm, which is so-called machine learning methods. So the machine learning methods are not concerned about the mathematical series and also physics or related domain series behind it. It's mostly concerned about the data. So you can use the same set of mathematical structure to describe the connectivity information about all the data points. And then you can keep training your model. Basically, the model is more or less about the connection and the mapping between one set of dataset to another dataset. The input dataset will be considered as a training dataset, and the output dataset are considered to be your target dataset. So with this training mechanism, you are tuning all your parameters to give you this mapping function that can map your expected input and expected output. And by doing that, you can create a mathematical model that could be plugged into a computer, and then this computer could be utilized to take a new dataset, and then you can make predictions. So when you're doing this, taking this machine learning paradigm, You don't need any physics-based series or any other domain-related series behind it. All you need to worry about is the distribution and association of all the data points, correlation, and those information will be used to help you to map your input data to your expected output data. That's all the machine learning methods are about. It's trying to create this mapping function, or some people call it approximator, to approximate the function can map your input to your output. There are basically 3 types of machine learning algorithms. The most commonly used one, I would say, would be probably supervised learning. That's the one we have been very familiar with in our daily life. And even though we are not doing all the training ourselves, but we are providing the data to help those big companies to train the model for us. For Face ID, Echo, that you use Alexa and use for Amazon, and also Google Home. Those are using the data captured on a daily basis to help detect all the information and structures embedded in the data you're providing. Could be audio clips, could be images, could be video clips. Those information will be used and have been used by all these vendors to provide fantastic products. The reason they are working well is because there are a lot of trained data with the labeled information. So when you have a data that's already labeled and you know what the output should be, then you have this capability to train your model to fix errors that might be predicting something wrong because you know the expected output. And then you can keep iterating and make your model better. So another machine learning algorithm that's mostly used by data mining related research is to train the model with unlabeled data. So the model will be able to divide your data into, mostly I'm talking about a clustering method, which is able to divide your data into different groups or categories. Even though they don't know what your data are, they can tell the difference between different groups. For example, if you have a group picture of horses and a group of picture of cats. For the unsupervised learning methods, the methods can tell you, there are some difference between 2 different groups, even though the method cannot tell you what each group is. It's up to you to decide if it's a horse or cat or something else. But it's able to tell the difference mainly because there are some intrinsic difference between these 2 types of data. So that's unsupervised learning, mostly clustering. Or you can do regression, which is more or less like a best fitting. So what you all do is trying to best fitting certain variables, mostly numerical values, to figure out the changing of one value, how that will be affecting the changing of another value. You are looking for a function that can help you to map some continuous value to another continuous value. So lastly, it's the reinforcement learning, which is commonly used in robotics. And there is no training data. The data will be accumulated when you're running. So in this reinforcement learning environment, the data is accumulated while the robot or any agent is running in action. It will take the input, and then based on some rewarding and penalty mechanisms, the model will learn how to deal with different situations. So for supervised learning, as I mentioned, there are basically 2 steps. First step is just simply training. You need to provide data, labeled data, and given the input, you have expected output. You already know the ground truth of your training data. Then you plug into some existing machine learning algorithm. So machine learning algorithm will try to figure out this function that can help you to map your input to your output, because you already know the output. So you have a lot of tools in numerical optimization and some other methods you can use numerically to help you to minimize the error between your predicted output and the expected output, which is the ground truth. So that's why the supervised learning highly depending on the quality of the data. If your data is not clean or it's not good, or your function you're trying to approximate will more or less give you something your data is pointing to. So it's highly depending on the quality of data. So you cannot expect a good machine learning model without a good quality of data providing the input for training. So after the model is ready, you can start testing it out using the so-called testing data, which is usually coming together with the training data set, but a good practice is to divide your data into mostly 70%, 80% of training data set, and the rest 30, 20% will be used for testing. So this testing data will not be used for training. Otherwise, it's just like someone train you with some problems that will be used in exams, and then test you again with those questions. And after training regressively with all those questions, you can easily get 100% accuracy. But that doesn't mean that you're good at solving those problems. So it's good practice to separate the training and testing data at the very beginning. And you never train your data with your testing data. You only test your model with your test data, and then you can have a confidence about how accurate and how good your model is performed. For unsupervised learning, here I'm just show you the example for clustering. When you have an input X, you don't know what that is, and clustering method will take it and trying to divide the data into multiple groups based on some definition of the error you provide, or some definition of the measurements you provide. For example, when you want to measure the difference between two classes, there should be a definition of something like a distance, so that when the algorithm goes into the data, they can explore the distance between two different data points and then give you the distance between different classes. And by doing that, it's able to cluster all the data points together, give you multiple classes for you to look into. As I mentioned, for the reinforcement learning, it's mostly used in robotics, autonomous vehicles research, and other things related with robots. So it has a rewarding mechanism. It has an agent that will be telling you if what you're doing here is good or bad. It has some reward and a penalty mechanism, so that whenever you did something good, it will give you some reward. So you have higher chance to do that again in the next time. So for different actions or different rewards and different penalties, so your agent is getting adaptive to the environment you're dealing with. So that's a way how the reinforcement learning is working. For this module, we are not going into details about reinforcement learning. It's a really exciting field to look into, as a lot of real-life cases could be categorized into reinforcement learning environment. For example, the self-driving cars and robotics, and there will be more and more of those in our daily lives. The algorithm itself is getting rapidly developed currently.